Okay, hello. So this is the first lecture here from Oberwolfach in the course on mean curvature flow and other evolution equations. As you know, I asked you to look at another lecture that is on this topic from myself on YouTube. So in that lecture, I think I might have been going very fast and I was only concentrating on mean curvature flow. So in this lecture now, I would like to look again at the evolution equations in a more general setting where you have a general speed and derive the evolution equations for curvature and the geometry of an evolving hypersurface and explain some of the properties of these equations. So the idea here is we look at the evolution of hypersurfaces in Riemannian manifolds. But of course, you can, in the first step, always think of the target manifold being just Euclidean space, if you like, and then the formula will get a bit simpler. But the basic ideas are the same. So we look at families of mappings from a domain manifold across some time interval into some other smooth Riemannian manifold of one dimension higher with a given smooth Riemannian metric G bar. So this is the Riemannian manifold, smooth and no boundary, say. And similarly, assume this has no boundary and is smooth. And then we want to look at evolution equations of the type ddt of the position vector at some time and point is equal to some speed, let's write minus f for this, times a unit normal point and time, and with some initial data. The basic problem we want to look at, and here, so the picture you should have in mind is, here's the manifold Mn, and here you have this map F at time t, and this maps into some target manifold Nn plus 1 bar, and we have some color here, and the manifold gets mapped into such a image, and this image is moving, and here you have a unit normal nu, which is the direction of the speed orthogonal to the hypersurface of length 1, and I have drawn it like this because if the hypersurface bounds a domain, I always take this nu to be the outer unit normal to the domain. And if you have this setup, then we would like to see what kind of interesting functions f we can look at. And the most geometrically natural things are when the f is a function of the second fundamental form. So here suppose that f is a function of the second fundamental form, which has entries ij with respect to an adapted orthonormal frame. So hij would be the derivative of the normal in tangential direction EI, and the common component taking in direction EJ again. So nu is normal, and E1 up to En are tangential vector fields of length 1. And then this is the definition of second fundamental form. And since the inner product of nu and Ej is 0, this is the same as minus nu gradient Ei in direction of Ej. And of course, this would be the covariant derivative with respect to the ambient manifold. And then we take here the tangential component and here the normal component. And then f is a scalar function. So we want f to be a symmetric function of the principal curvatures, that is the eigenvalues of Fij. So f is going to be a function of lambda 1 up to lambda n, and these lambda I are the principal curvatures that is the eigenvalues of the of Hij, this matrix with respect to the matrix Gij, the induced metric, Gij at some point P would be the inner product of the tangent vectors, the f dxi, the f dxj with respect to the matrix G bar. So it's the restriction of the metric in the ambient space to the tangent vectors in the tangent space of the hypersurface. And when I say eigenvalues, I mean the eigenvalues of this matrix with respect to that matrix, which are the eigenvalues of the Weingarten map. And the Weingarten map has the components h upper I lower j, and h upper I lower j is computed from the HJL by taking the inverse of the metric G Li, sum over L. So notice the important thing here is to distinguish between the second fundamental, which is a mapping from at the point P, from the product of the tangent space with itself to R, so it's a bilinear form, whereas this W can be considered as the associated map via the positive definite invertible matrix Gij of. So we can view the second fundamental form either as a bilinear form, and this would be this definition, or we can raise one index like here, then it becomes a map from the tangent space to itself with these DCs, and then the eigenvalues of this mapping are the principal curvatures, which is the same as saying the eigenvalues of this matrix with the respect to the metric Gij. So these are the key invariants really encoded in the two matrices Gij and Hij, or in the matrix H upper I lower j, and we want our function to depend on lambda 1 up to lambda n in a homogeneous and symmetric way. So maybe I put this still on this blackboard here. So we want f is homogeneous and symmetric in the lambda 1 to lambda n principal curvatures here. And the main examples are, of course, things like mean curvature, Gauss curvature, the classical geometric quantities that are studied for such a long time in differential geometry. So here are the main examples. For f, first one would be f equals the mean curvature, which is the sum of the principal curvatures. In some old books, you have the average of the principal curvatures. We always take the sum because this is the same as the trace of the second fundamental form with respect to G, which is the same as the trace of W, which is the same as G upper ij, H lower ij, which is the same as H upper I lower I sum over I. So this is the notation we're using, and this is the simplest choice, where f is the mean curvature, and then this flow would be the mean curvature flow. Now, the second possibility would be to take f to be the Gauss curvature, which is the product of lambda 1 up to lambda n. It's the Gauss curvature flow. So in this case, it is again symmetric, homogeneous, but now homogeneous of degree n rather than homogeneous of degree 1. We have a different speed, different behavior, and third one, you could take f to be any of the elementary symmetric functionals. You could take the sum over the lambda I1 up to lambda I m, and you do this over all tuples where I1 is less than I2 is less than IM, and then this is the elementary symmetric function of degree n, and it's again symmetric, homogeneous. So this would be the elementary functions. Now, of course, you could also take combinations of these, or you could take powers of these. So there's a lot of natural flows that you get just from these examples. But there's one which has come to quite some use in physics and general relativity. So let me mention this one. This is the inverse mean curvature flow, where you go in the other direction, but with speed 1 over h. So this is the so-called inverse mean curvature flow. Now, let me just note one thing. A very simple example in all of these flows is an example that you get when you start with a round sphere in Euclidean space. Then because of these symmetries, so if the initial hypersurface is a round sphere of some radius r0 sitting in Rn plus 1, then what you get from here, so these surfaces MNT will still be round spheres of some radius r of t, and then this radius will be satisfying an ODE depending on which of these speeds you have chosen. So for example, here you would get something like n over r on the right-hand side. ddt of position is mean curvature, and each principal curvature is 1 over r. So you get ddt of r is equal to minus n over r, whereas here you get ddt of r is minus 1 over r, sorry, here, minus 1 over r to the n. So in these cases, you immediately get examples of a sphere which is contracting in the first three cases, and a sphere which is expanding very fast in this case. So all these flows, because of the symmetry and homogeneity, have the properties to let spheres evolve as spheres, and the radius depends on the particular law that you have chosen here. Okay, so the setup that is quite general here, and now the question one can ask is, under what conditions do we have a chance to solve this? I told you one example where you can solve it, namely in the case where the initial surface is a sphere, but in general, of course, this may not be an equation that has a solution at all if you start with some initial hypersurface. It turns out that you can solve this if you start in particular with a hypersurface which is closed, which has no boundary, and if the flow that we just discussed is of a parabolic nature. Now, what does that mean, that this flow is of a parabolic nature? I don't want to go into all the details, but I'll at least give you the result. And parabolic means it's essentially like a heat equation. And so the simplest setup, suppose the initial hypersurface contained in an n plus 1 g bar is closed, which means no boundary, compact, sphere, torus, and smooth. Then does the flow ddt f equals minus f times nu have a solution for a short time. Okay. And starting with this initial hypersurface. So we start with the identity map, embedding this into the ambient manifold, and we want to ask, when do we get at least a short time solution, and hopefully a unique short time solution? So in other words, when can we get this flow started? And the answer is yes, if the flow is parabolic in the right way. And I don't want to go through the whole existence theory here and parabolic theory of parabolic equations, but I want to explain what parabolic means and make it plausible. So now, since f depends on the second fundamental form, we should understand how the second fundamental form depends on the mapping f. Clearly, because the second fundamental form comes from the derivative of the normal, and the normal is something like first derivatives of the position. The second fundamental form is a second order operator depending on the metric. And we want that second order operator on the right hand side to somehow be a Laplace equation, a heat equation, or more general, an elliptic operator acting on the position vector f. Now, this is made precise by when you write down the definition of the second fundamental form in terms of the coordinates, and that's the so-called Weingarten equation. So the Weingarten equations, they take the original definition that Hij is equal to the derivative of the normal on the one hand, but also equal to the normal component of the derivatives of the tangent vectors, and writes it in local coordinates. And it's easy to see that from this relation, when you spell it out in local coordinates, then it must be true that minus Hij times the alpha component of the normal vector in some coordinate system in the ambient space must be given exactly by the derivative of the position vector, of the tangent vector, but this means it comes from the second derivatives of the position vector. So we get here the minus sign, and then we get d2f dxi dxj. And then since it's a covariant derivative, we get with a minus sign. Sure, I get the signs right. Yes, with a minus sign, gamma k I j. So these are the Christoffel symbols of the induced metric G times the df dxk. And here I have the alphas component, so I should take the alphas component here. This is all you get in Euclidean space, but if you're in a Riemannian ambient space, you also get a connection coming from the ambient metric. So I write a bar here, alpha, beta, gamma times df, beta, dxi, df, gamma, dxj. So this is corresponding to the second formula, where you identify the second fundamental form as the normal component of the derivative of tangent vectors. The other formula you can write as that the derivative of the normal vector in a tangent direction made covariant by adding gamma bar, alpha, and now I have to get the indices right. Beta delta times df beta dxi times nu gamma, nu delta, sorry, delta. And this is then the component h I j index raised gj l df alpha dx l. Okay, so these are the equations that relate the second fundamental form to the second derivatives of the position vector. And now the dependence on the second derivatives of f determines whether our operator is elliptic or not on the right-hand side, and therefore whether the equation is parabolic or not. So, for example, when the speed is the mean curvature, then the speed is exactly the trace of this, right? Because the mean curvature is g upper ij times h lower ij. So the trace of this is exactly our speed vector. And then we would get this trace of this right-hand side. And the key thing would be whether this here is positive or not. So this would be the trace of the second derivatives here. So this would certainly be a nice elliptic operator. But there's something subtracted here because this also contains second derivatives of f. So I would have to check whether this is actually an elliptic operator. Turns out it is sufficiently elliptic that you can solve the equation for short time. Maybe I should write down what I just said. So in case of the curvature flow, then you have ddt of the position is equal to minus h times nu, which is, by the way, called the mean curvature vector. And from this formula, we get that h is equal to the trace of the second derivatives of f minus g Christoffel symbols ij df alpha dx k and plus gamma bar alpha beta gamma df beta dxi df gamma dxj. So this last term here is not so important for this consideration because it's lower order. It only involves first derivatives of f. Now, as I said, this is a nice trace of second derivatives. So this would be, right, so here I have to put the alpha and multiply the whole thing with nu to make it an invariant thing, to multiply this with nu beta g bar alpha beta, okay? And then it's a vector independent of the coordinate system. So the question here is in what sense this is elliptic. And it turns out that here the Christoffel symbols in this case, the gamma k g I j, as you may know, this is the g upper k l times ddxi g lower lj plus ddxj times g I L minus d dxl gij, and on the other hand, you know that gij is equal to the inner product of the tangent vectors, so of the first derivatives. So when you plug this second formula into here, do a little calculation, you find that you end up with exactly gkl times the inner product of the second derivatives of f with respect I xj times df dxl. In other words, you get exactly the tangential component of the second derivatives, and they are being subtracted here from the full second derivative. So we can write that the mean curvature vector is equal to the trace of the normal component of the second derivatives of f, like this, plus this lower order term. Ij, and now it turns out that this is enough, since our equation is invariant under tangential diffeomorphisms. It does not matter that we are missing here the trace of the second derivatives of the and their tangential component. It is enough that this is elliptic in the direction of the speed, which goes in normal direction. So it's an elliptic in normal in directions normal to the tangent space, which is the direction this. So in other words, one has to be a little bit careful about the fact that the right-hand side is an elliptic operator because of this freedom of tangential diffeomorphisms. Our equation doesn't change if we make a change of the coordinate system on the hypersurface. And that leads to this fact that the equation only is elliptic in this sense. But it turns out this concept of ellipticity is enough to make the equation parabolic and give you a smooth solution for a short time, no matter what your initial data are. So this fact that this equation is elliptic in this sense turns out to be enough to prove short-time existence. And I will not go through this precise proof of short-time existence because I did that in quite some detail in the previous course where I was discussing Ricci flow. So when you go through my lecture series on Ricci flow, also available on the website of the Oberwolfach Institute, then you find there in the, I think in the third lecture of that series, you find a detailed proof of the short-time existence where it's explained how these tangential diffeomorphisms come in and how you can deal with them. So here we just note a theorem. Mean curvature flow has a unique short-time solution for all closed, smooth initial data Mn0 sitting in a Riemannian ambient manifold, which is itself smooth in a smooth ambient manifold. So mean curvature flow is special in the sense that we don't need any further conditions, just smooth initial data closed, so we don't have to worry about boundary data or we don't have to worry about fall-off conditions near infinity. That would be a separate subject. And we always get a smooth solution for short time, and then we can start studying how this solution behaves. Now, for our more general flows, the result will not be that general, because we need this ellipticity, but we don't have just a trace with respect to such a positive definite matrix. In our general case, we have here a minus f times nu. So in general, our speed is ddtf equals minus f times nu. And f is some function depending on this matrix Hij, which is here in this bracket. So the question then is whether this dependence in the linearized setting is such that you get a positive definite matrix in front of this term. You see, this calculation here about the Christoffel symbol is the same for all of our speeds. But now we have something general here. So the key thing is the linearization. So that LF Ij di dju be the operator that comes from taking the derivative of f with respect to Hij, linearize, and then multiplied with these derivatives. If we define this like that, then we can write then the linearization of the flow starts with ddt g, let's take g is the linearization of f, and then we would get here minus f times nu. So we would get minus Hij, which is this term here. This is minus Hij, differentiating with respect to that. So we get exactly here LF Ij of d2f dxi dxj, and again the normal component plus lower order terms. Okay. Now, in the case of the Laplacian, so if f equals h, then Lij of f is exactly g upper ij. Because it's exactly if you differentiate f here with respect to the Hij, you are left with the g upper ij. So now, in order to argue that we again get short times existence, we need exactly that this operator here is positive definite at each point, which means that these derivatives here, that these derivatives of f with respect to Hij, that has to be a positive definite matrix everywhere. And that is then enough also to get short time existence. Let us state that as a theorem as well. So theorem, general case, suppose that df dHij at Pt is positive definite. Everywhere on the initial hypersurface, then the same conclusion holds as before. Then the flow ddt f equals minus f times nu has a short time, has a unique short time solution for any closed smooth initial data. For any such closed MN. So this is the key condition here, positive and definite. And the remark is, of course, that you can read that off from the eigenvalues. So remark df dHij positive definite is the same as checking that df d lambda I is positive for all I and for all p. In other words, you can consider f either as a function of the HIJs, depending on the whole matrix HIJ, or and GIJ, or you can view it as a function depending on the eigenvalues. And this little lemma is a good exercise, actually, to convince yourself that this thing here as a function of the HIJ being positive definite is exactly the same as saying that f considered as a function of the n principal curvatures is monotone with respect to each one of them. So now, for example, examples, you have if f equals h, then you have the f d lambda I, of course, is equal to 1 for all I. If f is equal to inverse mean curvature flow, minus 1 on h, then you have the f d lambda I is equal to 1 on h squared times 1 for all I. So it's positive if h is positive. So, for example, inverse mean curvature flow has smooth short time solutions if h is strictly positive on the initial surface. Have strictly positive mean curvature, then this assumption that 1 on h squared is positive everywhere is fulfilled, and you get a short time solution of inverse mean curvature flow. If you take f to be the Gauss curvature, then you get that df d lambda I is equal to 1 lambda 1, lambda 2, and so on, and then you skip the lambda I, and you get the lambda n. So this one is taken out. So this is positive if, for example, if the initial hypersurface is convex. So we get that Gauss curvature flow has a smooth solution whenever you have a strictly convex, smooth initial hypersurface. And so on. So you can, for each of these geometric evolution equations, use this criterion quite easily to see under what condition you get a unique, smooth, short time solution on some short time interval. Okay, that's how much I wanted to say about short time existence. Now, once you have such a short time existence result, the question comes, how does the solution change? How does the shape change? And for that, you need evolution equations for all the quantities. In that other lecture, I recommended to you last week, this computation has been done for mean curvature flow. So let's see how this works out in the general setting. So this is an important general lemma. Let me just, or theorem, if you like. I think it's important enough. So we formulate this theorem. Suppose f mn plus 0t to nn plus 1 g bar solves ddt of position vector is equal to minus speed f times a choice of unit normal. Then we have the following evolution equations. So first of all, we get that ddt of the induced metric on the hypersurface is equal to minus 2 times the speed times the second fundamental form. Then we get from there that ddt of the volume element, d mu, on the hypersurface, this is a well-known first variation formula, is minus the speed f times the mean curvature times the volume element. What's also important is that then ddt of the inverse metric gets a minus sign, so this is then plus 2f hij. So this gives you all information how the metric and the volume element changes on the surface. Then at the next step, it's important how the unit normal changes. It turns out the unit normal in this case is just changing in the direction of the gradient of f. So this is a tangential gradient of f. And then you get, most importantly, the next level. How does the curvature change? And this means the change of the second fundamental form. So the second fundamental form changes according to the Hessian of f, the covariant Hessian of f, with some extra terms, minus f times h I L h L j minus the Riemann tensor in the ambient manifold in normal direction. This is a 0, normal direction times j. So 0 is the nu direction in the ambient manifold. And sometimes it's also important to have one index raised. So let's write this here, ddt of h upper I lower j, so that's the Weingarten map. Then you get here upper I lower j of f. And then because you've raised one index, you get an extra term coming from this derivative of the inverse metric. And then comes with a plus sign and cancels this minus term. So you end up with plus F times H I L H L J plus R bar 0I 0J. And now we can take the trace and we get the last formula for ddt of the mean curvature, just taking the trace on both sides, and then you get the well-known Jacobi operator. On the right-hand side, you get Laplacian of f plus f times the full norm of the, here this is wrong, there's one index is up the I, so you get here the sum over I and j gives you the sum of all the squares of the entries. So this is the full norm squared of the second fundamental form. And then here, taking the trace over I and j gives you something that looks like the Ricci curvature in normal direction. And in fact, that is correct, because although this is not the full trace over I and j, the extra term, the trace, the term where we have 0, 0, does not contribute because it's antisymmetric in the first two and last two indices. So just taking the trace over I and j gives us the Ricci curvature in the ambient manifold in normal direction. And this is the evolution equation of the mean curvature. So this one blackboard really summarizes all the key properties for any deformation that you might want to do for a hypersurface in any Riemannian manifold. Captures all the information, how the induced metric changes, how the normal changes, how the second fundamental form changes, how the Weingarten map changes, and how the mean curvature changes. So this is sort of the fundamental result about deforming hypersurfaces in any Riemannian ambient manifold. And in fact, you can also do it in Lorentzian manifold and a couple of signs change, otherwise it's the same idea. So this is sort of a very fundamental result. It's just a computation, and I showed to you how to do it efficiently. But it's a key for understanding how the geometry of such a hypersurface changes when you move it according to a certain speed, f. And you've seen in that other lecture how to prove this theorem in the special case of f being the mean curvature. Let me just say what changes, actually not much. So proof ideas. Well, to prove one, you do ddt of gij is equal to ddt of the inner product of the tangent vectors, df, dxi, df, dxj, with respect to g bar. Now, when you write this out, this is ddt of sort of a big mess where you have g bar alpha beta at f of x times df alpha dxi df beta dxj. And you may think you have to differentiate all these terms, but see, here's the key trick for all these computations. You can sit yourself in a normal coordinate system on your hypersurface, xi, at a certain point, and you can assume that in your target manifold, you also have a normal coordinate system. So assume, without loss generality, that at P in Mn and f of P in Nn plus 1, we have local normal coordinates xi and y alpha. I between 1 and n, alpha between 0 and n. And then, you know, there, only at this one point, you get all the Christoffel symbols with respect to g equals 0 on all the derivatives of the metric equals 0. And similarly, you get the Christoffel symbols with respect to g bar, alpha, beta, gamma, equals 0 there, and all the derivatives with respect to y alpha of the ambient metric equal to 0 at this point. So this is at P, this is at f of P. Only at this point, not in the neighborhood. But you can assume at those points, this is 0. So I don't have to differentiate the first term because the derivative of g bar at this point where I'm doing the computation is 0. So I only do the derivative on the other two terms. And therefore, I get with this little computational trick, I get that ddt gij is equal to, and the coordinate system doesn't change, so I get, and it's clearly symmetric in I and j, so I get twice ddxi of ddtf, and ddtf is minus f times nu. Okay. And now, when I differentiate the first factor, I get a normal vector times a tangent vector, which is 0. So I only have to differentiate the second factor. So I get minus 2f times dxi of nu times df dxj with respect to g bar. But now you look at these Weingarten relations that I wrote down before. And there was a formula for the derivative of nu. And it involved also a Christoffel symbol in the ambient manifold. But at the point where I'm doing the computation, that is 0. So I can again ignore it. And then this here becomes exactly the second fundamental form hij. So I end up with minus 2f hij. Now you may say, oh, yeah, but you computed it only in that one coordinate system, not in a general coordinate system. That's true, but this is a tensor equation. This tensor here transforms under coordinate changes in exactly the same way as this tensor transforms. Therefore, if I have established this equation in one coordinate system, it has to hold true in all coordinate systems. So that's why it's such a good trick to choose a clever coordinate system, do the computation, and get a result that then holds in all possible coordinate systems. So we get this relation. All right, then from there, it's easy to get, well, the inverse is then clear, ddt of the inverse. This is the inverse of the matrix is always minus d upper IL, d upper jk times the inverse of the metric KL with respect to any smooth parameter t And then this is just the negative of this, 2f times h upper ij. That settles this. And then ddt of the volume element is ddt of the square root of the determinant of the metric g locally times dx in the coordinate system. And when you compute ddt of a determinant, you get the 1/2 times 1 on the square root of the determinant. And then you get ddt of the determinant is the cofactor matrix, which means you take the determinant times g upper ij times the time derivative of the matrix. And this times dx. And then the square root cancels, and now you insert the formula for ddt gij, and then this means you have to take the trace of hij, and you end up with the 2's cancel, you get minus f h times square root determinant g dx, which is minus f h as required. Okay, that settles the first 3 equations here on the board in the general setting. Now we have to go for the evolution equation of the unit normal. And key things to remember here is that you have that nu times nu is identically 1, and you have that nu times the f dxi is identically 0 for all I. So we can differentiate these relations and get 0 on the right-hand side. So this allows us in the first instance to conclude that 2 times ddt nu times nu is equal to 0, which means that ddt of nu just has tangential components. So this means we can decompose ddt nu as a sum of tangent vectors. We can decompose it like this. But now, because this is 0, I can pull the ddt on the other side. So I get here minus nu times ddt df. So this is ddxi of ddtf, and ddtf was minus f times nu. And this gets multiplied with g upper ij df dxj. And now notice, because of the Weingarten relation, ddxi of nu, remember that is a tangent vector, so it gets multiplied with nu, gives 0. So here I only have to differentiate with the f term. And if I differentiate the f term, the 2 minus signs go away. I get the gradient of f times 1. Nu times nu is 1. So I get gradient of f summed over all its tangential components. So this is exactly the tangential gradient of f as required. So that settles this formula. And now we have all the tools in order to compute the evolution equation of the second fundamental form. So now we take the formula ddt, right? We get from the Weingarten relation, we get minus hij is the normal component of the second derivatives of f, the Christoffel symbols with the respect to the metric g was a tangential term, and then there was still the Christoffel symbols here, that this is a vector, beta, gamma, df alpha df beta dxi df gamma dxj. So now to compute ddt of hij means we just have to take minus ddt of this. So we get minus the gradient of f multiplied with the Hessian of f dxi dxj plus the gamma bar beta gamma df beta dxi df gamma dxj. And right, and then we have to differentiate this one, so we get minus nu times the second derivatives of minus f times nu. And we put the ddt onto this term here. There's the minus sign, there's another minus sign from the f times nu, so this is differentiating this. And then here, remember with our trick again, because I'm differentiating at a point where this is 0, I only have to differentiate the first term, not the last two terms. So I get only one extra term. This is a minus sign, which is ddt of gamma bar, I'll not put an index in, alpha, beta, gamma, df, beta, dxi, df, gamma, dxj, and this gets multiplied with nu beta times g bar alpha beta. Okay. Okay. Now, at the point where I'm doing the computation, again, this term is 0. So at the point where I'm doing the computation, that term is 0. And this one here, because of the Weingarten relations, has a tangential term which comes from the Christoffel symbols of the gamma of the metric G. And this one here is the second derivatives of f with a plus sign. So, and here's a minus sign times the gamma term. The gamma bar terms is 0. So this term here is exactly the thing that combines with this term here to give me a second covariant derivatives of f. So we get here on the right-hand side exactly plus di djf. This takes care of this term and this term. When the second derivatives falls onto the f. But then there are some extra terms. So there's the second derivatives falling on the nu. When the first derivative falls onto f and one derivative is on the nu, then we get a tangent vector times the normal vector is 0. So the only other terms, both these derivatives fall on nu. So we get here plus nu times the second derivatives dxi dxj of nu times f. And then it remains to insert this term here. And now this derivative here, this gives a differentiating by the chain rule, this gives a derivative of gamma bar alpha beta gamma with respect to the y coordinate, say y sigma, multiplied with df beta dx I df gamma dxj. Okay, that's what you get. All right, now here we have to use the Weingarten equations again. Then when you use the Weingarten equation, you get a curvature term in the first instance and a derivative of Christoffel symbols, which gets differentiated once more. And then we have two derivatives of the Christoffel symbols in the ambient manifold. And those two derivatives of Christoffel symbols, they are not zero. The derivatives of the Christoffel symbols combine exactly to give you the curvature term that was ascertained in the theorem. And the other term that you get from here is exactly the square of the second fundamental form when you use the Weingarten equation twice. So I leave that as an exercise and just give you, write down the result again. This is equal to the Hessian, the IDJF, and then we get, as I claimed, minus F HIL HLJ minus R bar 0I 0J. And then we repeat again, this last term here comes from the derivative of the two derivative terms coming from the Christoffel symbols. Right, I forgot something here. I took only wrote down the first part of the chain rule. Right? I took the derivative and then I have to take the time derivative of y, but the time derivative of y was minus f times the normal. So there's a new sigma here. So yeah, sorry. Now it's correct. So I claim this term here combines exactly with this term here, with the term coming from here in order to give you this curvature term. And I leave that as an exercise. Okay, that is a derivation of the main curvature quantities that you get in the main first theorem. And now once you have that theorem, you can use the commutator identities that are being discussed by Stephen Lynch in order to get sort of equations which can be more easily seen to be parabolic. But I leave that for next time. So next time we start with this formula for the second fundamental form and use the commutator identities in order to replace this Hessian of f with an elliptic operator acting on the Hij, so that you see that Hij itself satisfies a parabolic system of reaction diffusion equations. So we do that next time. Thank you.